Lesson 4-8, direct and inverse variation. And in this lesson, you'll learn to solve problems involving direct and inverse variation. It's important because you can use direct and inverse variation to solve problems involving work and music. Let's take a look at this real-world application, water usage. Do you find yourself singing in the shower? If you are like the average American, you have enough time to sing several songs. Okay, the national average for time spent in the shower is 12.2 minutes. A standard shower head uses about 6 gallons of water per minute. That means you use 73.2 gallons of water for each shower you take. Taking one shower per day for 1 year would use 26,718 gallons of water. Okay, so the number of gallons of water used depends directly on the amount of time spent in the shower. The table shows the number of gallons of water used as a function of time in the shower X. Okay, so the word directly is already a clue that we are going to talk about a direct variation problem. Okay, so it says here that table below shows the number of gallons of water used Y as a function of time in the shower X. Okay, so the number of gallons depends basically, if you rephrase that sentence, the number of gallons you use will be dependent upon the number of minutes you spend in the shower. So for 3 minutes you use up 18 gallons of water, 6 minutes 36, and so on and so forth. 15 gallons would be 90 gallons of water. Okay, so the relationship between the number of minutes in the shower and the gallons of water used is shown by the equation y equals 6 times x, where x represents the number of minutes. Okay, this type of equation is called a direct variation equation. We say that y varies directly as x, or y is directly proportional to x. So this equation tells you two things. That one thing actually, and you can say it two ways, that y varies directly as x, or y is directly proportional to x. This means as x increases in value, y increases in value, or as x decreases in value, y decreases in value as well. And we go to the definition of direct variation. A direct variation is described by an equation in the form y equals kx, where k is not equal to 0. Okay, so in the equation y equals kx, the k is called the constant of the variation. To find the constant of the variation, we simply divide each side by x. So just like in solving an equation, we divide both sides by x and we end up with y over x equals k, and that's how you find the constant of the variation. So look at example number 1. Let's see how we use this formula. Julio's average wage varies directly as the number of hours that he works. If his wages for 5 hours are $29.75, how will they be for 30 hours? Okay, so again, when you talk about Julio's wages vary directly as the number of hours that he works, and we go back to the definition here, and we say that in this case that y varies directly as x. So that means in this case, when you talk about Julio's wages, our y will be Julio's wages, and the number of hours that he works will be our x. Okay, so first find Julio's hourly pay. Let x be the number of hours Julio works, and let y be Julio's pay. Find the value of k in the equation y equals kx. So in this case, we are looking for the constant of the variation. So the value of k is the amount of money Julio is paid per hour. Okay, so let's see how this works. And formula for k will be y over x. Okay, and we simply substitute the value. Julio's wages varies directly as the number of hours he works. If his wages for 5 hours are $29.79, that means our y is $29.75, and we have $5 for his hourly on the number of hours that he works. Okay, then K would be $5.95. 29.75 divided by 5 will be 5.95. So Julio is paid $5.95 per hour. But that's not what the problem is asking for. It's asking how much will they be for 30 hours of work. So we continue with our problem. We know now that the constant of our variation is $5.95 or 5.95. Next, find out how much Julio's wages will be for 30 hours. Okay. We use the formula now for direct variation, which is y equals kx, and we know what k is, which is $5.95. We also know what x is, which is $30. So we simply multiply 5.95 times 30 will give us 178.5. Therefore, if Julio worked for 30 hours, his wages will be $178.50. Okay? Now let's analyze the formula, okay, and see what else we can come up with that formula. Let's analyze the first example. And the first example, using the table in the application at the beginning of the lesson, many proportions can be formed. Two examples are shown below, and these are the two examples. Okay, you have and this is the table. We can do 3 over 18 equals 9 over 54. 6 over 36 equals 9 over 54. You can equate all of these ratios because they're all in proportion. So the number of minutes we can put as the numerator, and the number of, or the gallons of water we can put as the denominator. So we can write a ratio of 3 over 18 equals 9 over 54. Another way we can do this is that instead of putting the number of minutes in the numerator and the number of gallons in the denominator, we can actually make the number of minutes as the numerator and denominator right here, and the gallons as the other ratio. So the number of minutes will be one ratio, the number of gallons of water will be another ratio, which looks something like this. So your number of minutes will be 3 over 9, and 8 over 54 will be your gallons of water. So those are two examples how you can create a proportion from that table. Okay, so two general forms of proportion like these can be derived from the equation y equals kx. So if we let x1 and y1 be the solution for y equals kx, let the second solution be x2, y2. Then we have now y1 equals k, y sub 1 equals k x sub 1, and y sub 2 is equal to k x sub 2. Okay? Now, knowing that these are all equivalent, okay, we can use the equation first, y sub 1 equals k x sub 1. We know that this describes a direct variation equation. We can use the division property to divide both sides by k x sub 2 and y sub 2 because they are all equivalent to each other. Use the division property of equality since y2 and y sub 2 and kx sub 2 are equivalent. You can divide the left side by y sub 2 and the right side by kx sub 2. Doing so, we end up with this proportion, or that equation right there. Okay, get out of there, get out of there. Okay, if we simplify that, okay, we come up with another formula for direct variation. So with this, okay, write this down because this is another formula that you can use for direct variation. Okay, now let's find out another formula which you can use for direct variation. Another proportion that can be derived from this proportion, okay, will be that. So let's say that you have x2, y1, x1, y2 by finding the cross products of these. So if we do that and divide both sides by y1 and y sub 2, Remember, whatever you divide to one side, you need to divide to the other side to make them equal. And if we simplify this, this is what we come up with. So x over 2 over y over 2 equals x over 1 over y over 1. Another formula for direct variation. There you go. So you have three formulas. Okay, the first one is y equals kx. Oops, sorry. Let me remove that. Y equals kx. Why is that now red? Let's put that back in black. Which is also the same as, if you want to solve for the constant of variation, k equals y over x. So, first formula, second formula, these are all formulas that you can use for direct variation problems. Now let's take a look at example number 2 and see how this applies. Okay, taking a look at example number 2, if y varies directly as x and y equals 28, okay, when x equals 7, find x when y equals 52. So let us use y sub 1 over y sub 2 equals x sub 1 over x sub 2, equation number 2. Okay, and let's substitute values. Okay, if we let y sub 1 equals 28, x sub 1 equals 7, and y sub 2 equals 52, and substitute it to that equation, we end up with 28 over 52 equals 7 over x sub 2. And using cross products, we end up with this equation, 28x sub 2 equals 7 times 52, and we end up with 52 times 7 will be 364, dividing both sides by 28, x sub 2 is now equal to 13. So when x is equal to 13, y is equal to 52. And that's how you use that particular equation to solve this direct variation problem. Okay? And the opposite of a direct variation problem, or the reverse, is an inverse variation. We say that y varies inversely as x. This simply means that as x increases in value, y decreases in value, or as y decreases in value, x increases in value. Remember, we talked about this in science, in direct variation. Okay, oh, why am I getting a highlighter? In direct variation, your graph is basically a positive graph. In an inverse variation, your graph is a negative sloping graph. Okay, so going back here, for example, the more miles you drive, the less gasoline you have in the tank. That's a perfect example of an inverse variation problem. And if we define inverse variation, an inverse variation is described by an equation of the form xy equals k, where k is not equal to 0. Sometimes inverse variation are written in the form of y equals k over x if we solve for the variable y. If we solve for the variable y, wherein we divide both sides by x, we end up with this equation. So that's the first equation that we need to know when you talk about inverse variation problems. Okay, let's take a look at how we apply this formula. In example number 3, the length of a violin string varies inversely as the frequency of its vibrations. So in this case, we know right away what is y and what is x, because in this equation, okay, it says here that y varies inversely as x. So in this case, the length of a violin string varies inversely as the frequency of the vibrations. That means the length of the violin string is your y, and the frequency of the vibrations of its vibrations will be your x. Okay, let's go back to the problem. A violin string 10 inches long vibrates at a frequency of 512 cycles per second. Find the frequency of an 8-inch string. So just like example number 1, okay, let's create a let statement. Let L represent the length in inches and F represent the frequency in cycles per second. So we want to find the value of K, or we want to find the constant of the variation, just like in example number 1. So we write down our inverse variation equation, which is LF equals K. Okay, so knowing that equation, we substitute the values 10 and 512, 10 inches, 512 cycles per second. We find our constant of our variation, which is 5,120. Now, using the constant of the variation, okay, we can find the frequency in cycles per second of an 8-inch string. So how do we do that? Again, let's write down the formula for inverse variation. LF equals K, okay? Because length varies inversely with the frequency of its vibration. So substituting the values, we have an 8-inch string multiplied by F times the constant is equal to the constant of the variation, and simply divide both sides by 8. We end up with 640. So the frequency, okay, of an 8-inch string is 640 cycles per second. And just like in a direct variation equation, we can find another equation for our inverse variation equation. Okay, so let x1 and y1 be a solution for the inverse variation of xy equals k, and again let x2 y2 be a second solution for and then we know that x sub 1 y sub 1 equals k, and x sub 2 y sub 2 equals k, because those are both solutions. Okay, so if we equate them to each other, okay, we know that this is our inverse variation equation, and then what we do is substitute x sub 2 y sub 2 for k, because they are equivalent. Now we have x sub 1 y sub 1 equals x sub 2 y sub 2. Okay, so this is now another formula we can use for an inverse variation equation. Okay, and this equation, x sub 1 y sub 1 x sub 2 y sub 2, is called the product rule of inverse variations. Okay, now let's see how we can use this to create proportions. Okay, and let's divide both sides of that, okay, with x sub 2 y sub 2, because they are all solutions, so we can actually divide both sides of the equation with x sub 2 y sub 2, and then we simplify that. We end up with x sub 1 y sub x sub 2 all over is equal to, let me restate that, x sub 1 all over x sub 2 is equal to y sub 2 all over y sub 1. Notice that this proportion is different from the proportion for direct variation. Now this will become confusing because although they look the same, okay, the formula for inverse variation is not the same. So if you use the wrong formula, obviously you will get the wrong answer. Now how do you use this formula? Okay, so you have now, before we go to example 4, you have 3 equations for inverse variation. Okay, and memorize those equations as you go along. You can use either the product rule or the proportion rule to solve problems involving inverse variation. So you can either use this formula right here, okay, or this formula. This is the product rule, okay, or the proportion rule, the bottom part, to solve problems involving inverse variation. Let's take a look at this example, example number 4. If y varies inversely as x, okay, and y is equal to 5 when x equals to 15, find x when y equals to 3. Okay, so you have an inverse variation problem. What I would suggest you to do is you label them right now. This is y sub 1, x sub 1, and this is y sub 2, you want to find x sub 2. Okay, and let's take a look at method 1. Use the product rule. X sub 1 y sub 1 equals x sub 2 y sub 2. Okay, that's the product rule. Substitute our values. You end up with 15 times 5. Okay, 15 times 5, x sub 1 would be 15, and y sub 1 would be 5. Okay? And alright, sorry for the pause there. So x sub 1 y sub 1, which will be 15 times 5, is equal to x sub 2, which we're trying to find, multiplied by 3, which is y sub 2. So using that and simplifying 15 times 5 and dividing both sides by 3, we end up with 75 over 3. Okay, so x sub 2 will be equal to 25. Using method 2, the proportion rule, we now have x sub 1 over x sub 2 all over y sub 2 over y sub 1. That is the proportion rule formula. And then we simply substitute the values of x sub 1, x sub 2. We have 15 over x sub 2, which we're trying to find, and we have 3 over 5. Using cross products, we end up with 75 equals 3x sub 2. Divide both sides by 3. We still end up with 25. Okay? And let's take a look at the last example. In the last example, okay, we're going to talk about simple machines. If you have observed people on a seesaw, you may have noticed that the heavier person must sit close to the fulcrum or pivot point to balance the seesaw. A seesaw is a type of a lever, and all lever problems involve inverse variation. And this is a simple machine. Suppose weights W sub 1 and W sub 2 are placed on a lever at distances D sub 1 and D sub 2, respectively from the fulcrum. Okay, and this is how it looks like. So you have weights W sub 1 and W sub 2. They're placed on the lever at distances D sub 1 and D sub 2, respectively from the fulcrum, and this is your fulcrum right here. The lever is balanced when W sub 1 and D times D sub 1 is equal to W sub 2, D sub 2. This is, if you notice this formula, it is an inverse variation formula. This property of levers is illustrated at the right. Okay? Okay, when you ride on a seesaw, believe it or not, you're actually doing math. So the fulcrum is placed in the middle of a 20-foot seesaw. Colina, who weighs 120 pounds, is seated 9 feet from the fulcrum. How far from the fulcrum should Antonio sit if he weighs 135 pounds? Okay, so to make this seesaw balance, it's asking how far Antonio needs to sit to make them balance. So let's represent let's define our variables. Let W sub 1 be equal to 120, which is the weight of Colina. D sub 1 which will be the distance of Colina, which is 9 feet from the fulcrum. W sub 2 is Antonio's weight, and we want to find out the distance of Antonio from the fulcrum so that the seesaw will be balanced. Okay, using the formula, we simply substitute the values. 120 times 9 equals 135 times D sub 2. Simplifying 120 times 9, 1080, okay, equals 135 D sub 2. Dividing both sides by 135, we end up with D equals 8. So in this case, for the seesaw to be balanced, Antonio should sit 8 feet from the fulcrum. Alright, boys and girls, that's the end of the lesson. Thank you for watching.